This is Physics 2120, Lecture 30. Today we're going to talk about interference of light waves. The first thing I want to talk about is something called Lloyd's mirror. An arrangement for producing an interference pattern with a single light source is called Lloyd's mirror. So we have a real source of light, and we have a mirror down on the bottom, so that creates a virtual source of light. And so then as waves come and hit this viewing screen, we actually get an interference pattern because the reflected ray acts as if it's coming from S. And so this looks like a two-slit experiment, only all using a single source and a mirror. So the arrangement can be thought up as a double-slit source with a distance between S and S prime comparable to the length d. So we get an interference pattern. However, the positions of the dark and bright fringes are reversed in this pattern of two real sources. And that's because there's a 180-degree phase change produced by reflection. So an electromagnetic wave undergoes a phase change of 180 degrees upon reflection from a medium of higher index of refraction than the one it was traveling in. So it's analogous to the pulse on a string reflected from a rigid support. So if I'm traveling in air, say, and I hit glass and I reflect, that reflection causes a 180 degrees phase change of the light source. However, there is no phase change when the wave is reflected from a boundary leading to a medium of lower index of refraction. And that's kind of like a pulse on a string when we had the free support. So as the wave comes in and is reflected, there is no phase change at that boundary. Now, one of the ways that we see this is something called thin film interference. We often see these in thin films like soap bubbles or oil on water. We get varied colors are observed when white light is incident on such films, and they're going to result from the interference of waves reflected from the two surfaces of the film. So some facts to remember when dealing with thin films. Electromagnetic wave traveling from a medium of index of refraction N1 to N2 undergoes a phase change when N2 is bigger than N1, no phase change when N2 is less than N1. And also remember, the wavelength of light in a medium with an index of refraction N changes. So lambda sub N refers to the wavelength inside some medium of, that has an index of refraction, where lambda is the wavelength of light in air or in a vacuum. So as we look at an actual thin film problem, we're going to assume first that the light rays are traveling in air nearly normal to the two surfaces of the film. So ray 1 is going to undergo a phase change as it reflects off the top of the film. Ray 2 goes through and is reflected off the bottom, and at this point there's no there's no phase change in the reflection. So it comes back up and comes out. Of course, this ray also comes down, and we can get a reflection here with no phase change as it comes through. So we can look at what happens to the light that's reflected and what happens to the light that is transmitted through the thin film. Ray 2 also traveled an additional distance of twice the thickness of the film before the waves recombine. So twice the thickness, that's the distance, has to equal to m plus a half times the wavelength of light inside the medium. That is the condition for constructive interference. The plus 1/2 is because one of the rays of light had a 180 degree phase change on reflection. So for constructive interference, 2nt is equal to m plus a half lambda, or m can be 0, 1, or 2. For destructive interference, we don't want the extra half wavelength, so 2nt is equal to m lambda. Now, these equations are used for a very specific situation of a thin film that has a higher index of refraction than the material on either side. If I had a thin film, say, of oil on water, I would have to consider the second wave might also have a 180-degree phase shift. So every thin film problem we need to look at individually. These are not universal equations. So two factors influence interference: possible phase reversals on reflection and differences in distance traveled. The conditions that above are valid for the medium above the top surface is the same as the medium below the bottom surface. Again, if there are different media, these conditions are valid only as long as the index of refraction for both is less than n, which is the index of refraction of the thin film. If the thin film is between two different media, one of lower index of refraction than the film and one of higher index, the conditions for constructive and destructive interference are reversed. We have to check the conditions for each specific problem. With different materials on either side of the film, you may have a situation in which there's a 180-degree phase change at both surfaces or at neither surface. Be sure and check both the path length and the phase change through the thin film. Here we see an example of light reflected off of a thin film. These are some soap bubbles in air, and we see all sorts of different colors as the thickness of the thin film changes slightly, and as it changes slightly we're getting constructive interference for different wavelengths. And so in this area here we're getting constructive interference for the wavelength of red light, whereas in here we're getting constructive interference for green light. And as the thickness of the thin film changes, we see this swirling of colors. Another method for viewing interference is to place a plano-convex lens on top of a flat glass surface. The air film between the glass surfaces varies in thickness from 0 at the point of contact to some thickness t. A pattern of light and dark rings is observed, and those rings are called Newton's rings. The particle model of light could not explain the origin of these rings. So Newton's rings can be used to test optical lenses. So as we see light coming through the plano-convex glass, some of it's reflected off the surface, some of it goes through and is reflected off this surface, and as someone looks, we're going to see these ring patterns as we get alternating constructive and destructive interference. So how do we solve problems with thin films? First, identify what the thin film causing the interference is. Look at the type of interference, constructive or destructive, that occurs, and that's determined by the phase relationship between the upper and lower surfaces. Phase differences have two causes: differences in distances traveled and phase changing on reflections. Both causes must be considered when determining the constructive or destructive interference. The interference is constructive if the path difference is an integral multiple of lambda, or the wavelength, and destructive if the path difference is an odd half multiple of lambda. So let's look at a specific problem. Calculate the minimum thickness of a soap bubble film that results in constructive interference in the reflected light if the film is illuminated with light whose wavelength in free space is 600 nanometers. So this is the condition that we used in our example before, where we have a thin film with air on either side. So we can use the equation 2nt is equal to m plus a half lambda. So the minimum would be when m is equal to 1, or the thickness is lambda over 4n, which is going to be 600 over 4 times 1.33 is 113 nanometers. It's the thickness of the film. So look at a different problem. A non-reflective coating. A silicon solar cell, silicon has an index of refraction of 3.5, uses 550 nanometers light to generate electricity. A silicon monoxide, N equals 1.45, coating, is placed on the solar cell to minimize reflections of that specific wavelength of light. What is the minimum thickness of the coating? So So first, let's look at the conditions. So as light comes in from air onto the silicon oxide, the reflected light has a 180-degree phase change because the N is going from low to high. Then after the thin film here, we get another reflection, and again I get a 180-degree phase change because I'm going from a lower index of refraction to a higher index of refraction. There's no phase change as I move through the boundary, only when I'm reflected on a boundary. So now I'm looking at the thickness here to determine the number of wavelengths that I need. Since these two both have a 180-degree phase change, I need the distance inside the silicon oxide to be an integral multiple of the wavelength of light in the silicon oxide. So the path difference is going to be the wavelength of light in it over 2 is the minimum distance for destructive interference. So twice the thickness is equal to delta, which is lambda n over 2, which is lambda over 2n, or solving for the thickness, we get 94.8 nanometers is the minimum thickness to have destructive interference on reflection. What does that mean? If there's destructive interference on reflection, so we're getting no light reflected here, all of the light must go through. So that's how a non-reflective coating works, is I make sure that there is no reflection, and if there's no reflection, since energy has to be conserved, all of the light, all the energy has to go through the thin film. Now the Michelson interferometer was invented by American physicist A.A. Michelson. The interferometer splits light into 2 parts and then recombines the parts to form an interference pattern. And this device can be used to measure wavelengths or other lengths with great precision. So it works by having a light source where the light is split into 2 rays by this half-shaded mirror M0, and it sits at a 45-degree angle to the incident beam. It's called a beam splitter. So half the light is reflected, half the light is transmitted. The reflected ray went towards mirror 1, the transmitted ray went to mirror 2. So the 2 rays travel separate paths, L1 and L2. And after reflecting from the mirrors, they eventually recombine at the half-shaded mirror, and they're going to form an interference pattern. The interference condition for the 2 rays is determined by their path length difference. So one of the mirrors is movable. As it moves, the fringe patterns of bright and dark bands collapses or expands depending on the direction M1 is moved. The fringe pattern shifts by 1/2 a fringe each time M1 is moved a distance of lambda over 4. So the wavelength of the light is then measured by counting the number of fringe shifts for a given displacement of a mirror. Now Michelson used his interferometer to disprove the idea that the Earth moves through an ether, which was this imaginary substance that light waves had to travel on, since we knew all waves travel on a medium, like water waves travel in water or sound waves in air. We know now that that's not true, and that electromagnetic waves the electric wave rides on the magnetic, and the magnetic wave rides on the electric wave. But it still has modern applications, and one is the Laser Interferometer Gravitational Wave Observatory, or LIGO. So general relativity predicts the existence of something called a gravitational wave, which is a wave moving through space which compresses and decompresses space itself. So in Einstein's theory, gravity is equivalent to a distortion of space, and those distortions can propagate through space. And the LIGO apparatus is designed to detect the distortion produced by a disturbance that passes near the Earth. The interferometer uses laser beams that have an effective path length of several kilometers. At the end of an arm of the interferometer, a mirror is mounted on a massive pendulum. So when a gravitational wave passes, the pendulum moves, and the interference pattern due to the laser beams for the 2 arms changes. So here's a picture of LIGO. It's in Richland, Washington. And this building here is a fairly big building. and it has all the apparatus. And then these are the arms of the interferometer, huge, long. And inside you see this these tubes that the light travels down. At the end there's the mirrors. These tubes are kept in a vacuum, and so we've got this huge vacuum chamber with this interferometer, and as a gravitational wave goes by, one of these two orthogonal arms would compress or expand slightly and show a difference in the interference pattern. So, to review what we talked about today, we talked about interference of thin films. There's a 180-degree phase change upon reflection, going from a low index of refraction to a high one. 0-degree phase change upon reflection, from going from a high index of refraction to a low one. And we must remember that the wavelength changes inside different substances. And lastly, we talked a little bit about interferometers and how they work.